Hello everyone, in this video we will begin Unit 3, Probability Distributions. So the first step will be to discuss discrete probability distribution. So that's when the random variable is discrete. Then the first definition that we need in this video is what is a random variable. So it's pretty much a function that will associate a real number with an element in the sample space. So remember that the sample space can be anything, right? So we have used some sample space, or we have like head or tail. So we can use letters, we can use different symbols, or like the strings, text strings. Then what we do with the random variable is that we translate that information into a real number. So the way in which we denote a random variable is using capital letters, mainly the letter X, the letter Y, or the letter Z. Those are like the most popular names that we use to describe a random variable. So here is an example. Statisticians use sampling plans to either accept or reject batches of or lots of material. Suppose one of these sampling plans involves sampling independently 10 items. So 10 items are drawn from 100, that's the whole batch. And we know that there are 12 defective items in the whole batch. In the 100 units, there are 12 that are defective. So X, which is the random variable here, is defined as the number of items found defective in the sample. That means in the 10 items. So X quantifies the number of defective items. That means that our X, or random variable, can take values from 0. 0 means that in the sample we don't have defective items. 1 defective, 2 defectives, up to the maximum value is 10, right? Because the sample size is 10 and we know that there are 12 defectives in total. So it is possible to take up to 10 defective items. Okay, let's check this second example. So the sample space when 3 chips are tested and classified as defective and non-defective. So we have 3 chips, right? So each chip has 2 alternatives, either is non-defective or defective. Therefore, in the first position, there are two possibilities. In the second, 2 possibilities. In the third chip, there are 2 possibilities, right? That's 2 to the power of 3, 8. So there are 8 sample points in the sample space. And as we said earlier in this video, please notice that the names or each point is represented by a string of letters. N means the 3 items are non-defective. ND means the 2 first are non-defective, but the third one is defective, right? That's the interpretation of each sample point. So if we define our random variable as the number of defective chips, then there are 4 options here, or 4 possible values. 0 defective. 0 defective will be the first case, right? All of them are non-defective. 1 defective, that will be these 3 cases, right? 2 means 2 defective chips, and 3 defective, that there is only 1 point that satisfies as the last point in the sample space, right? So we can summarize that information here in this table. So for each sample point, we have the outcome in the random variable, right? So remember, the random variable is a function that translates sample points into an outcome of a variable using a real number. In this case, the numbers are going to be discrete because the first part of the discussion is discrete probability distribution. So we will take care mainly of those probability distributions that are using discrete variables. Now, in general, we will have discrete, but we may have also continuous random variables. So the distinction is the same as we have discussed in previous units. So discrete is when you can count. So if you're using a counting process, so most likely your random variable is a discrete random variable because you have number of, right? Integer numbers. Now, if you're taking measurements, then and you have decimals, most likely you will have a continuous random variable. we will have some specific probability distribution. So even though in this first video we will go over the general concepts of probability distribution, discrete, there are some specific probability distributions that will be applied and they have different applications. So in the case of the discrete, we will cover later discrete uniform, the binomial probability distribution, which is very popular, Poisson geometric, negative binomial, and hypergeometric. In the case of the continuous probability distribution, the most popular probability distribution in statistics is the normal distribution. It's like the most common probability distribution out there. A lot of models actually rely on the assumption that the data follows a normal distribution. And there are other probability distributions such as exponential, gamma, chi-square, log normal, and Weibull, and we will go over most of them. Okay, so the next concept that we need to define is what is the discrete, what is the probability distribution or the probability mass function. So we will call probability function the set of ordered pairs x, where x is the outcome of the random variable, and this fx here is a function, of course, of the random variable and represents the probability. That's the probability for that specific outcome. So there are some like basic properties. The first one is that fx is the probability is greater than or equal 0, and of course if you add up the fx for every single outcome of the variable, it has to be equal to 1. You already know that, right? Fx, it's the same thing as the probability, as the third characteristic here. So the way in which we represent these pairs, you know, like the outcome and the probability for each pair will be using tables, plots, or even some equations. So let's see an example and how we can create these probability distributions for the discrete case. So if a coin is tossed 3 times, find the probability distribution of the variable that counts the number of heads. So the random variable here is number of heads, right? That's the random variable. The sample space, how many points will have that sample space? It's similar to a chips problem. So if there are, in this case, there are 3 times, you are tossing the coin 3 times, and each time it has 2 outcomes. So that's 2 to the power of 3, it's like 2 times 2 times 2. Alright, then the sample space is given by all the possibilities. So let's say that we don't have heads, that's the 3, in the 3 times you get a tail. In the second one we might have 1 head. So let's write down all the possibilities with only 1 head. Right now, all the sample points where we have 2 heads. And of course, the last sample point will be when we have 3 heads. Alright, so in total, there are 8 sample points. There are 8 sample points, right? So now we can summarize them using a table. So for each outcome of the random variable, so what are the outcomes here? Remember that the random variable translates the sample space into numbers, right? Real numbers. So in this case, the possibilities are 0 heads, 1 head, up to 3 heads, right? 0, 1, 2, and 3. I missed the 2 here. So there are 4 possibilities, and fx will be the probability for each outcome of the variable. So x equal to 0, then how many sample points will give you x equal to 0? There is only 1. T means that there are 0 heads. So there is only 1 point out of 8. So the probability is 1/8. Then x equal to 1, we have 1, 2, 3. There are 3 sample points where we have a single head, right? So this is 3/8. Now for x equal to 2, there are 3 sample points with 2 heads. So same probability as the previous one, 3/8. And the last one, there is only 1 point, right? 1/8. If we add them up for every single x, you can check that it is equal to 1, right? It is equal to 1. And of course, every single probability is greater than or equal 0. Therefore, it satisfies the conditions that were defined here in order to get the probability distribution. So you can use, if you want, a bar plot also to represent the function, but the table is fine. The table is a good way to represent it, especially when you have few possible values here. Okay, let's check an example where we test the knowledge of the probability distribution. A shipment of 20 similar laptop computers to a retail outlet contains 3 that are defective. If a school makes a random purchase of 2 of these computers, find the probability distribution for the number of defectives. So the interest is in the number of defectives. Therefore, x, it's the random variable, will be number of defective computers, right, that the school is gonna get when they buy the 2 machines. Now, what are the possible values of x? So x can be equal to 0 when there are non-defective laptops for the school. 1 if there is only 1, or 2 because this is up to 2 because they are buying 2 laptops, right? So it is not possible to get more than 2, even though in the whole batch there are 3 defectives. All right, so now we need to get the probabilities. So the first probability for 0 is the probability that x, the random variable, is equal to 0. So we need different things. First, we need to find in how many cases, in how many scenarios x is equal to 0, and also we need to compute how many possibilities we have in the sample space. So remember that the structure of the problem, so there are 20 items in total, and the school is gonna buy 2, right? So the total number of possibilities here, or selections of the computers, is out of the 20, the school is gonna get 2. It's gonna select 2. It doesn't matter the order here. It doesn't matter the order, right? What matters is like which computers are selected. That's it. But there is no like first or second position here. Okay, so this is for the number of points in the sample space, right? 20 combination 2. Now we need to get the number of points where x is equal to 0. So what is the meaning of x is equal to 0? Remember that there are 20 computers, they are buying 2, and there are 3 defectives in total. So from the 3 defectives, they are getting none because x is equal to 0 in this case, right? So from the 17 remaining computers, these are like good computers, they are okay, right? Because there are only 3 defectives. So it is expected that they are gonna get 2, right? Because again, x is equal to 0 in this case. So from the defective computer, they get 0, and from the good computer, they get 2. So that's how they find the probability. You can get a probability of 0.715 and more decimals. Probability of x equal to 1 means that the school will get the probability of getting 1 defective laptop. So number of sample points, same thing, right? 20 combination 2. There are 20 laptops in total. They are gonna buy 2, so it's a selection where the order doesn't matter. Now from the 3 defective laptops that are in the whole batch, in this case, since x is equal to 1, then they will get 1, right? So 1 is taken from there. And you need to consider also the good computers, right? So out of the 17, they are gonna get also 1 good computer. I want you to notice that here the sum of the upper part of the number of elements, it's equal to the total number of elements, right? And the selection in the numerator, when you add them up, it's equal to the items that are selected in the denominator. So that's not a coincidence. That's not a coincidence. That's a structure. All right. So let's compute this probability. So this is when x is equal to 1, this is 0.268. And the last one, probability of x equal to 2. It has a similar structure, right? 20 combination 2, total number of sample points in the sample space. So from the 3 effective, now they are getting 2, x equal to 2. And of course, from the good computers, they get 0. So this is when they are really unlucky, right? That they get, all of them are damaged. Okay, so this is 0.015. So if you want, you can create, as I said, the table x and fx for the values when x is equal to 0. The probability is 0.71. It has more decimals. When x is equal to 1, the probability is 0.268. And when x is equal to 2, you get the remaining probability. If you use all the decimals, when you add them up, you will get that the sum is equal to 1. Okay, let's check the last example in this first video. So the experiment, it's saying that 3 people or 3 persons are selected from 4 men and 2 women. So there are like 6 people in total and 3 are selected, 3 are picked. The random variable here of interest is that the number of men selected, So since you are selecting 3 people, then the possibilities are 1, 2, and 3. So why, maybe you're asking yourself why 0 is not an option for this variable. That's because there are only 2 women. And since you are selecting 3 people in total, then you can pick the 2 women, but you will need one man to be able to fill the 3 people in total. Alright, so it's just 1, 2, and 3. Just 1, 2, and 3. Okay, so now we can get the probabilities. So the number of the points in the sample space, please notice that it has a similar structure compared to our previous problem. So there are 6, we have 6 people in total and we are selecting 3 of them, right? So 6 combination 3 equal to 20, that's the number of sample points. That means all the possibilities that we have, like the number of selections that can be performed in this case. Alright, so this is number of points in the sample space, 20. Remember that we need this for the denominator in the probabilities. And now we can find the number of points in the numerator. So when x is equal to 1, that means when 1 man is selected. So in how many points that happen? If there are 4, we have 4 men and we select only 1, and from the 2 women, 2 are selected. So from the 6 people in total, we have selection of 3, right? 1 man and 2 women. That's when x is equal to 1. Alright, similar idea for when x is equal to 2. So from the 4 men, 2 are selected, x equal to 2. Remember that x is the number of men selected. And of course, from the women, only 1 is selected. So to complete the 3, 2 men and 1 woman. There are 12 possibilities for that. And when x is equal to 3, means that 3 men are selected. So that means that from the 4 men, 3 are selected, and from the 2 women, 0 are selected. So there are 4 options, or 4 ways to do that. So following the same idea, the same structure, you can find the probabilities x equal to 1. It's going to be 4 divided by 20, right? Or if you want to write the whole expression down, so it's like 4, 1. So we take 1 man, and 2 women over the total number of options, 6, 3. And that's how we get the probabilities here. 4 divided by 20, 12 divided or 20, and 4 again over 20. So here we have the probabilities, 0.2, 0.6, and 0.2. So when we add them up, this is 1, right? And we can present it in different formats. We can use table, we can use plot, and even we can use equations. So this is the table format, outcome of the variable, and the probability, outcome and the probability. This is using a bar chart. So we have the x values 1, 2, and 3 men. And the probabilities, right? For 1 man, the probability is 0.2. For x equal to 2, the probability is 0.6. And for x equal to 3, the probability is 0.2 again. And the last way in which we can represent this probability distribution is by using an equation. So if we check this pattern here, and let me write down the expression for the second one. For x equal to 2, for x is equal to 2, this will be from 4 we take 2, from 2 we take 1, and 6 combination 3. So the denominator will remain the same, 6 combination 3, it won't change. Even for x equal to 3, again, the number of of points in the sample space is the same, right? But now you can check up in the numerator, we can identify some patterns. So here, for example, it's equal to x, right? So if we do x equal to 3, then we will get from 4 we take 3, right? So this is from 4 we take x if we want to make it general. Now, in the case of the second combination, we have 2, from 2 we take 2, and then from 2 we take 1, so it's decreasing. It is decreasing. So one way to generalize that is from 2 we take 3 minus x. If we do that, then from 2 we take 3 minus x. When x is equal to 1, then this expression is equal to 2, right? And if x is equal to 2, then 3 minus x is equal to 1. And of course, for the last one, 3 minus x, when x is equal to 3, is going to be equal to 0. So in that way, we can write down the expression, an equation that's going to represent the probability distribution or the probability mass function. So we're using 3 different alternatives: table, the plot, and we're using a formula to represent the PMF. Okay guys, this is everything in this video. I'll see you in the second part.